Hello friends, welcome to my channel. Here with me Ziad Snosi. Before I start in this video or in this lecture, if any one of you, my friends, wants to get in touch with me asking for help or codes or explanation of my previous lectures, you can find me on Fiverr. That's my reference on Fiverr, or you can directly email me or contact me on WhatsApp. Today we have an optimization problem, as you can see, max z. It's a maximization problem equal to 10x1 plus 8x2, and subject to, we have two constraints here, 2x1 plus 4x2 less than or equal 36, and 4x1 plus 2x2 less than 48, and we have x1 x2. This ranging two variable should be greater than 0. So we need to find the optimal solution. We need to find x1 and x2, which makes z as maximum as possible and satisfies these constraints. And we have to know, we have to be careful that x1 and x2 both be positive values. Alright, so we use the linear programming method when the number of variables is two or more. Okay, so in this case we have two variables problem. Okay, so it satisfies this condition. And the second one, all constraints should be of type less than or equal. Okay, and this also this example satisfies this condition. And the right hand side of the constraints, which are 36 and 48, are both positive. So this example satisfies all these three points, which is fit for the linear programming. Okay, so okay, our procedure now, we have some points here. So just before I start with the procedure, I need to note that it's the simplex. It's the most frequent technique used in linear programming, but there's also a graphical method, but it's limited with the dimension of the problem, of the optimization problem. When the dimension is getting higher, it's hard to visualize. For example, if it is more than 3, so it's impossible to visualize it in the computer. So we use a simplex method. This method can deal with this kind of problem when the variable dimension getting higher. So in this technique, simplex method, we add another variables which is called slack variables. We will see an example of how to apply this. And note that all constraints in this optimization problem are linear, and also the objective function is also linear. The loss inequality, which is x1 and x2, which is greater than or equal 0, is special one. While it's not a constraint in the same sense of the others, it just forces the solution to be a non-negative value. Okay. We will see how to make, because it's a simple problem, we can visualize it. I can use Matlab to visualize this problem, so I will show you the feasible region for this problem. Okay, so observe the feasible region is bounded by x1, x2 and the two constraints. Okay, any points inside this feasible region is called feasible solutions. And very important to conclude that the optimal solution will always fall in one of the vertices of this region. Okay, so in our example we have 4 vertices. It is then clear that one way to solve this linear programming is to find the value of x1, x2 at these vertices, and from these compute the value of objective function at each vertex of this region. More commonly it's also called the corner points, and then select which point give me maximum of z. Okay, so we have two constraints. The first one, which is 2x1 plus 4x2, which is less than or equal 36. We need to draw this constraint. Just I need to make x2 on one side you will divide by 4 and take this on the other side. It will be x2 less than or equal 9 minus 5 x1. Okay, this is, we get this blue line. Alright, this is the first constraint. Okay, the second one, the second constraint, which is 4x1 plus 2x2, which is less than or equal 48. We need to take x2 on one side, so it will be divided by 2 the all sides, and take this to the other side, right hand side, so it will be less than or equal 24 minus 2x1. So we got this constraint. I'll give you the code how to draw these lines into Matlab. Okay, you will find in the description below. So we have these, we have this line or this constraint and this constraint, and we also have x1 greater than or equal 0 and x2 greater than or equal 0. So this is my case, this x1, this x1, and this line is x2. Okay, so whenever x1 is we take this region for x1 and this region for x2. This is the blue constraint, this is the red line. Okay, so our feasible region will be in this is our feasible region. Okay, and we have 4 corner points, which is this one and this one, the origin, and this one and this one. Okay, so the solution, the optimal solution, will be one of these 4 points or these 4 corners, and any points inside this feasible region will call feasible solution. Okay. Okay, we have some steps we need to start in order to solve a linear programming optimization problem using Simplex method. We have 7 points here. The first one, we change the optimization equation or the optimization problem into standard form. You have the constraints and the objective function, you need to make it in standard form. Second point, equate the objective function to 0. The third point, construct a table of for the objective function and the constraints. We'll work on this first one, these 3 points, and then we will make the others. Okay, the fourth point will be extract the internal variable. 5, extract the external variable, and we need to exchange between these. We'll see the example, and find the common element and obtain the optimal solution. Alright, let's get started. So we need to make the first 3 procedure. We need to put the constraint and the objective function or this optimization problem into standard form, and equate second one, equate the objective function to 0, and third one is to construct the table. Okay, so we have the first constraint, and we add the slack variable, which is x3, and make it equal to 36. This is the procedure. Second one, we make 4x1 plus 2x2 plus x4, which is another slack variable, because we have 2 constraints here, will be equal to 48, and x1, x2, and the others, the 2 slack variable will be greater than or equal 0. This is the form. Okay, we also need the objective function. We write it in this way, which is 10x1 plus 8x2 plus x3. In some reference you will find 0 times x3 plus 0 times x4, but leave it in this way. So this is the standard form we'll be using in linear programming, Simplex method. Okay, this is the form of Simplex method, how to apply Simplex method to solve a linear programming optimization problem. Alright, the second point is to equate this objective function to 0. So just you need to multiply all these equations by minus sign, so you get this minus x3 minus x4 will be equal to 0. Okay, so this is the second point in our procedure. Alright, Okay, third point in the procedure, we construct a table and we make it in this way. So you need to add x1, all your variables, x2, and the two slack variables you added, x3 and x4. And you, in this row, you make the slack variables, which is x3 and x4. And here you have z. And here the right hand side will take of the coefficients. Okay, so you fill this table. You have here 2, and the second one is 4, the third one is 1, and the coefficient of x4 is 0, and the right hand side is 36, and so on. For 8, the coefficient of z you need to put here -10. The coefficient of x1, which is -10, and -8, and here you have to make 0. Okay, this is the procedure, and here is 0. Okay, so we make the third step in our procedure. We make this table, which takes the objective function and two constraints. Okay, after we complete the 3 steps of the procedure, we go to the step number 4, which is extracting the internal variable. Before we extract the external variable, I need to note that we have here an identity matrix. If we have 3 slack variable, for example x3, x4, or x5, you'll find 1, 1, 1 in the column. Alright, okay, so back to extracting internal variable that corresponding to the largest negative number or the smallest number of row z. So you go to the row z, this one, and you find out which one is the smallest or the biggest negative one, which is in this case will be this one, -10. So you go to the column, so internal variable would be x1. Okay, I hope this is clear. Okay, step number 5, which is extracting the internal variable. We obtain the external variable by dividing the right side, the whole element of right hand side, by the elements of the internal variable x1. So you have 36 over 2. Okay, we'll see it here. You find all element of right hand side divided by the element of internal variable, 36 divided by 2, and as you can see, and you get 18, and 48 divided by 4, and you get 12, and you check which one is less. Which one is less, 12 or 18? So 12 is less than 18, so x4 will be the external variable and will be exchanged by the internal variable, which is x1. External variable. So this one, and we have this column. The common element, as you can see, is the overlap between these two, which is 4. The overlap between the internal variable column and the external variable row, the 4 will be as common element, and we will use this element in the next steps. Okay, now write a new table. Make the same variables here, x1, x2, x3, and x4, and here we have right hand side, and we go to the rows, we have x3, and here we have x1, not x4, because x4 was replaced by the internal variable, which is x1. Okay, and we substitute In this new table, we substitute the x4 replaced by x1, external by internal variable. Okay. Okay, now the new x1 will be the previous x4 divided by the common element, which is 4. Okay, I repeat, the new x1 here in the new table will be the previous x4, the previous external variable row divided by the common element. Okay, so 4 divided by 4, 1, 2 divided by 4 will be half, 0.25, and the right hand side which is 48 divided by 4, which is equal to 12. Okay, here we have z. So we need to find the new row of x3 and new row of z in this new table. Okay, you need to focus on this point. This, as I said, this is new x1, a new table. Alright? Okay. So new x3 row will be, you take the element above the common element, which is 2 in the negative sign of it. No, not negative sign. And you take the, if it is 2, you take minus 2. If it is minus 2, you take 2. Okay, the opposite sign. Okay. So you take opposite sign of 2 times the row of new x1, the entire row of x1 row. Okay, 0.5, and you can add 12 as well. Okay, so minus 2 minus 1 0. Minus 24. Okay, after that you need to add this row to the previous row of x3, and the result will be put in the new row of x3 in the new table. So I write it down, the previous row of x3, 0, 3, 1, minus 0.5, and here we have 12. So the result will be the new row of x3 in the new table, which is 0, 3, 1, minus 0.5, and 12. Okay, same idea will be make it for z row, for z row. So the new z row will be the previous z row. Okay, the new z row will be, take this in the same column of the common variable, which is 10. Take it in the opposite sign, which is positive 10 times the previous x, the new x1, and add the result with previous z, and the answer will be new z. I hope you understand. This is the maybe this is the complicated part of this linear programming simplex method. So you take 10 times the new x1, you get 10, you get 5, you get 0, you get 2.5, and you get 120, 2.5, you get 120. So you add this with the previous z, and the answer will be put in the new z in the new table. So this is the previous z row, previous z row, I mean, not 0. There's 0, and you add these two rows together. So the first element will be 0, minus 3, 0, 2.5, and 120. So this is the new z row. Okay, just I need to write it in the new table. Okay, 0, minus 3, 0, 2.5 and 120. Okay, so we complete this step. Okay, after complete the table, just we need to summarize what we have done in this last step. We divide the entire row of x4 by the common element of 4 and put the result in new x1, as you can see here in this table. Okay, and we find out the x3, new x3 row and the new z row. We see the video, and we check. Now we need to check the values of row z. If any of the z row values is negative, then we need to repeat the process. What does it mean by repeating the process? Which is find the internal variable and external variable, common element, and divide the right hand side, and so on. Okay, until we obtain the result. Until we obtain the whole element of z row is positive, then we terminate the program and obtain the result. Okay, you will find the code for solving this problem using Matlab in the comment section below, and I will make the other steps. Okay, so because we have here -3, this one, because we have here in this in the row of z we have negative sign, we need to repeat the process. Okay, what does it mean by repeating the process? We need to find the internal variable and external variable and common element. Okay, so because we have here -3, so directly the internal variable will be x2. Okay, because it's corresponding to the to the largest negative number of this elements. Okay, so -3 is of course is less than 0, so it will correspond to x2, so x2 will be internal variable. Okay, this column, mark it here, and we need to find the external variable. How to find external variable? We need to divide the whole elements of the right hand side, these two elements, by the elements of internal variable. So 12 divided by 3 will be equal to 4, and 12 divided by half, 12 divided by half, we'll get 24. Of course 4 is less than 24, so we have this row here, let's mark it. Okay, and we have this common element, and x3 will be external variable and will be replaced by x2. Okay, let me write a new table here. Here we have the same x1, x2, x3, x4. Here we exchange or replace x3 by x2, so we have here x2 and we have the same x1. You see here we begin with the select variable, and now we have the problem variable, optimization variable. Okay, here we have the right hand side, and here we have z. Okay, so first we need to find the new row of x2. We have this x3, so the new of x2 will be x3 divided by the common element, which is 3. So 0 divided by 3 will be 0, 3 divided by 3 will be 1, 1 divided by 3. Okay, let's leave it like so, and -0.5 divided by 3. Okay, and we have 12 divided by 3, which is equal to 4. Okay, we find this new x2 row. We find it how we find it, because we have we have this this is the internal variable. We have the internal variable, which is x2, and the external variable was x3, so we exchanged x2 by x3 in this new table, and we find x2. How we find it? We divide by the common element, which is 3 in this case. So we divide x3. How we find x2? New x2 was x3 divided by common element, which is 3. Common element between the internal and the external variable. Okay, so we got this row. The second row of x1, we find out x1. This is, sorry, x2. Now we need to find x1. This new x1. Okay, so new x1 will be previous x1 plus this number, which is 0.5 with negative, with opposite sign, which is minus 0.5 times the new of x2, new row of x2. Okay, how is that? We need to make this first, which is minus 0.5 times row of x2, so row of new x2 here, which is 0, 1 over 3 minus 0.5 over 3 and 4. Okay, what we got? We got minus 0.5 sorry 0 minus 0.5 minus 0.0165 0.08 3 and minus 2. Okay, we add this with the so we make this multiplication, and we need to add it to the previous this is previous of x1, which is 1/2, which is 1/2 0 0.25 and 12. Got the new x1 here 0 here minus 0.165, here we have 0.33, and here we got 10. Okay, just we write it here 1 0 minus 0.165, and here we have 0.3 and here we have 10. Okay, same idea with z. So new z would be equal to previous of z, previous of z, plus, you need to see, because we have here z, it was 3, so because this is the column of the internal variable, so we take this with opposite sign, which is 3 positive, times the new row of x2, new x2 row, which is this one, x2 new. Okay, just we take this first, 3 times new x2, 0, 1/3 over 3 and 4, we got 0, 3, 1, and we got here 12. So you need to add it with the previous z, which was 0 minus 3, it was 0 minus 3, 0, 2.5, and 120. Okay, got 0, got here 0, got here 1, got here 2, got here 132. Okay, just write it here, got 0, 0, 1, 2, 1, 2, 132. Okay, as you can see here, all these are non-negative, so we terminate the program, we terminate our system, and we find out our solution for this optimization, which is this one will be assigned to this, and this value will be assigned to this variable. So x1 will be 10 and x2 will be 4. Okay, I made this optimization problem solved in Matlab. Okay, for example, okay, this one. Okay, you'll find in the attachment below, in the description below. You can download it. Just make LP linear programming for our system, and you find the result. Okay, this 2 iterations, because we terminated with non-negative numbers here, and we have this the value for x1 and this value for x2. Okay, will give me the maximum result, which is 132. Okay, this is the first step, as you can see, -3 here. So we make it again and again. And I also made was graphical for showing these constraints. We have these 2 constraints, and we have this axis which is x2 and this axis which x1, and we have this feasible region, and we have these corner or feasible solutions, which the result was this one, which is as we see, linear programming was the result 10 and 4. Okay, graphical. Okay, if you can see with me, this point, this is not part of solution, this was part of solution, yes. So just solve this one. So this one, yeah, this corner, because the solution, the solution, as I said earlier, that it's one of these corner points. Okay, so it's x1 is 10 and x2 is 4. I hope this explanation helping you in solving linear programming. As I told you in the beginning of this video, if you have any problems regarding these optimization tasks, linear or non-linear, you can contact me on Fiverr or email me. Okay, thank you for watching.